Hello, AP Stat students. In Unit 5, we talked about sampling distributions of proportions and means. And in this chapter, in this unit, we are going to continue talking about proportions. That's our primary focus. I will throw in some problems with means, but mostly it will be on proportions. And this first part is from Chapter 8, and it is called Estimating with Confidence. And we are going to start with what is known as a point estimate. And it is a single number and it's derived from a sample statistic. So either p hat or x bar. So a single number derived from a sample statistic. To estimate a population parameter. So that population parameter is going to be p or mu. It is our best guess at the value of an unknown parameter. Let's look at some examples. In each of the following settings, determine the point estimator you would use and calculate the value of that point estimate. So, example A, the makers of a new golf ball want to estimate the median distance the new balls will travel when hit by a mechanical driver. They select a random sample of 10 balls and measure the distance each ball travels after being hit by a mechanical driver. Here are the distances. And it's not really giving any units, but I'm going to assume it's yards. So for this particular problem, it's talking about the median. So the point estimator is the median. Of our sample. And since these are not in order, we need to put them in order to find the median from smallest to largest. So let's do that. So we have 282. Then we have 284. 284 again. 285. Another 285. 286. Oh, I'm sorry, I see another 285. Then the 286. 287. 288 and 290. And let's find the median. So we're looking at the fifth and sixth numbers. So 1, 2, 3, 4, 5. And here would be the median. So the middle of 285 is 285. So the median is, so our point estimate value is 285. Right. B. The golf ball manufacturer would also like to investigate the variability of the distance traveled by the golf balls by estimating the interquartile range. So our point estimator here is going to be our interquartile range. And if you remember from first semester, IQR is the third quartile minus the first quartile. So to find the third quartile, it would be the median of the upper half of our data. So look at the 5 values. This would be our Q3. Oops. That's Q3. And this would be Q1. So our interquartile range, 287 minus 284 is 3. Right, and our last one. The math department wants to know what proportion of the students owns a graphing calculator. So they take a random sample of 100 students and find that 28 own a graphing calculator. So our point estimator here is our proportion, and the proportion is from the sample. So the correct notation would be p hat. And that value is 28 over 100, which is 0.28. And so that's the idea of point estimators and point estimates. Now, those are going to come into play with confidence intervals. So that's our next topic. Since our point estimate is probably not exact, but somewhere close to the true parameter, we can estimate an interval that we are pretty confident the true parameter lies in. This interval is known as the confidence interval. The amount of confidence we have in that interval is called the confidence level. The confidence interval consists of the point estimate plus or minus a margin of error, which we'll talk about later. The margin of error tells us how close the estimate tends to be to the unknown parameter. In repeated random sampling. Confidence level gives the overall success rate of the method for calculating the confidence interval. So in C% of all possible samples, the method would yield an interval that captures the true parameter. When we create a confidence interval, it's really important to be able to interpret the meaning of the confidence level we used and the interval that was obtained. Basically, the confidence level refers to the long-term success rate of the method. That is basically how often does this type of interval capture the parameter of interest. A specific confidence interval gives a range of plausible values for the parameter of interest. So confidence level doesn't tell us the chance that a particular confidence interval captures the population parameter. It tells us how likely the method we are using will produce an interval that includes the parameter if we use it many times. Right. If you look over here, this stuff is basically right, all of that. So this is the interpretation of the confidence level. And this is the interval interpretation. When we do our problems, this will really, really come into play. Right now, this is just an introduction. Looking at this diagram, this is a sampling distribution. So going back to our sampling samples. So here's our sampling distribution with all the means. And then right here is the true parameter. This is the mean. These, and it doesn't matter how many samples there actually are. There's 25 of these, but this is our true parameter. And over here, you have these green lines and you have these blue lines. What each line is each line is an interval from a sample. And if you look at all the lines, the green lines capture the true parameter, whereas the blue line, that lone blue line, misses the true parameter. The others capture it. Now, you can go ahead and figure out how many there are. I think there's 25. But before, like, you could have said that this is 95% of the intervals contain the true value, the true parameter. And confidence level usually is 90% or higher because that's the one that's chosen. But with the higher confidence, you are going to have a wider interval, and that might not tell us anything. So it's really important to pick a confidence level that gives us some important information about our data and not just a bunch of work that we do and doesn't tell us anything. So for this particular one, I would say 95%. So if we took many, many samples, about 95% of the resulting confidence levels would capture mu. So that's an interpretation of the confidence level. Okay, now let's go over here and actually do some examples. So you get, or do one example, and I'll toss in another one if we need to. How does the fat content of brand X hot dogs vary? To find out, researchers measured the fat content in grams of a random sample of 10 brand X hot dogs. A 95% confidence interval for the population standard deviation is 2.84 to 7.55. So this is our interval. Okay. Interpret the confidence interval. So going back to the first page, we are 95% confident that the interval from 2.84 to 7.55 captures and you don't just say the true parameter, tell what the parameter is. So in this case, captures the actual or the true standard deviation of the fat content of brand X hot dogs. Interpret the confidence level. 95% of all possible samples of size 10, because that was our sample size, will result in an interval that captures the actual standard deviation. And you will have more that you can do on your assignment. But another example I can give you, say there's a political pollster plans to randomly select, let's just say 500 voters, whether or not they support a particular candidate. The pollster will then take the results of the sample and construct a 90% confidence interval for the true proportion of all voters who support the candidate. So how would you interpret that? And so basically you can interpret it if the pollster repeats this process many, many, many times, then about 90% of the intervals that will be produced will capture the true proportion of voters who support the candidate. So that is another sample. And then lastly, true or false. The interval from 2.84 to 7.55 has a 95% chance of containing the actual population standard deviation, sigma. And this is false. And it's not that hard to wrap your head around this, and it's not that important, but just note that the confidence interval does not talk about probability or chance. So that never talks about probability or chance because the probability is going to be 1 or 0. You're going to have it's either going to capture it or it's not. So that does not talk about right? So the actual value is the value. I mean, it captures it or it doesn't. The probability is 1 or 0. 95% of the intervals will capture it. Okay, like I mentioned earlier, the price we pay for greater confidence, so if we increase our confidence, we will have a wider interval, which might not tell us anything about the population. And our last little thing is how to calculate a confidence interval. So the confidence interval is the statistic, which is your point estimate we mentioned at the beginning. So it's going to be your X bar or P hat. In this unit, we'll be concerned with P hat, plus or minus a margin of error. And the margin of error is found by taking what is known as a critical value and multiplying it by the standard deviation of the statistic. So this is the margin of error. That's what I'll label it as. The critical value depends on both the confidence level C and the sampling distribution of the statistic. And we will calculate a confidence interval in next time. Critical value is tied to the confidence level. Greater confidence requires greater critical values. And that's a wider interval. Standard deviation of the statistic depends on the sample size n. Larger samples, remember, give more precise estimates. We learned that larger samples means less variability. And less variability means smaller interval. In the statistic. Therefore, margin of error gets smaller when the confidence level decreases. The sample size n increases. But this is also could be more costly and time consuming. And those are your notes for 8.1a. Have a great day, AP Stat students.